Section 11.2 is on probability. Probability measures how likely it is for an event to occur. A probability of 1 or 100% means that the event is certain to happen. A probability of 0 or 0% means that it is impossible for the event to occur. Experimental probability is calculated based on data from observations or trials, and it is defined as the following. The notation here means the probability of this event occurring is the number of times the event occurs divided by the number of trials. So here's an example. You observe 119 animals at the zoo. 19 of them have wings. What is the experimental probability that an animal at this zoo has wings? So the number of times that the event occurs, well, you see 19 animals with wings, and the number of trials, that's the total number of animals, which is 119. Plugging that into your calculator and then turning that into a percent, that's about a 16% probability that an animal at this zoo has wings. The set of all possible outcomes of an experiment is called the sample space. When each outcome in a sample space has the same chance of occurring, the outcomes are considered to be equally likely. For example, rolling a die has 6 equally likely outcomes. When you roll a die, you can get a 1, a 2, a 3, a 4, a 5, or a 6, and all of those are equally likely to come up. If a sample space has n equally likely outcomes and an event A occurs in m of these outcomes, then the theoretical probability of an event is as follows. The probability of A occurring is m divided by n. So in other words, the number of outcomes divided by the number of equally likely or total possible outcomes. Let's take a look at a couple examples here. So what is the theoretical probability of each event? Rolling a number less than 3 on a die. So on a die, the only numbers that are less than 3 are 1 and 2. So I have 2 possible outcomes out of 6 total outcomes, or the probability is 1/3. Sometimes we express probability as a fraction, sometimes as a decimal, sometimes as a percent. So, you could say it's approximately 33%. What is the theoretical probability of rolling 2 dice and getting a sum that is a multiple of 4? Okay, so I'm rolling 2 dice and I'm adding them up. What is the probability that when I add those 2 numbers, I get a multiple of 4? So the smallest I can get when I roll 2 dice is a 2. 1 plus 1 is 2. The largest I can get is a 12. 6 plus 6 is 12. So the number of multiples of 4 in there are, I could roll a 4, I could roll an 8, or I could roll a 12. Okay, so how many different ways are there to roll a 4? Well, I could roll a 1 on the first die and a 3 on the second. I could roll a 2 on the first die and a 2 on the second. And I could roll a 3 on the first die and a 1 on the second. Okay, so there's 3 different ways to roll a 4. How many different ways are there to roll an 8? Well, I can roll a 2 and a 6, a 3 and a 5, a 4 and a 4, a 5 and a 3. Notice that 3 and 5 and 3 are not the same because 5 occurs on the first die and then a 3 occurs on the first die. And then the last one is a 6 and a 2. And there's only one way to roll a 12, and that's a 6 and 6. So that is 3 plus 5 plus 1, so that's 9 possible ways to roll a multiple of 4. And there are 36 possible outcomes when you roll dice, a pair of dice. So that's 1/4, probability of 1/4, or 25%. Sometimes there are too many equally likely outcomes to count. In that case, you can use something called combinatorics, that is, using the fundamental counting principle and permutations and combinations to find the theoretical probability. So here's an example, and it's a little complicated, but that's okay, we can do this. What is the theoretical probability of being dealt exactly 3/8 in a 5-card hand from a standard deck of cards? Sounds like you're playing poker, and so what's the probability when they deal you the 5 cards that you're going to get 3/8? Okay, so then let's write a few of these things out here. So the number of combinations, I'm going to abbreviate here, of 3/8, okay, from 4/8, Oops. I'm going to write that out a little more neatly, sorry. Let's do 3/8 from 4/8 is equal to 4C3. Okay, let's go over what that means. So in a standard deck of cards, there are 4/8. So what is the probability, or how many different combinations, how many ways can I get 3 out of those 4/8? So since the order doesn't matter, it's a combination, there's 4 possible 8s, and I need to get 3 of them. Okay, so that's my first 3 cards, or the 3/8. Then we need to find out what are the number of combinations of 2, and that's 2 because I have the 3 cards plus the 2 cards makes a total of 5 cards, of 2 non-8s from the other 4 cards. Oh, from the other 48 cards. So I need 2 more cards from the deck. There are 48 cards that are not 8s in the deck. So the number of combinations there is going to be 48C2. Okay, so now multiplying those two using the fundamental counting principle, I'm going to come up with the number of combinations of 5 cards, not combinations, I'm sorry, just the number of 5 card hands with 3/8. Okay, and then 2 other cards. So that's going to be 4C3 times 48C2, and that's just using the fundamental counting principle. Okay, so that's what's going to be on top of my fraction. Now I need to find the number of possible 5 card hands. So it doesn't matter what's in the deck, but how many different cans can I get? Well, there are 52 cards in the deck. Order doesn't matter, and I'm going to be dealt 5 of them. Okay, so let's go ahead and write our probability statement here. So the probability of a hand with 3/8 okay, is 4C3 times 48C2. So that was the number of 5 card hands that have 3/8 and 2 other cards that are not 8s, divided by 52C5, the number of possible 5 card hands. Doesn't matter what card I get, just how many 5 card hands are there. So I'm going to plug those numbers into my calculator, and I'm going to get 4 times 1128 on top over, oh wow, this ends up being 2,598,960. And then when I do that division of the multiplication and division of my calculator, I get 0.0017, which is approximately equal to 0.17%. So a very low probability of getting 3/8 dealt to you when you're dealt 5 cards. And the last thing we're going to take a look at here is called geometric probability. And you may remember this from geometry last year. And this involves length, area, or volume. So here's an example. A carnival game consists of throwing darts at a board with concentric circles. The larger circle has a radius of 8 inches, and the inner circle has a radius of 3 inches. What is the geometric probability that a dart thrown at random will hit the inner circle? Well, always in geometry, I like to draw a picture. So try to draw a couple circles here. There's my outer circle. There's my inner circle. Okay, not totally drawn to scale. And this here, this radius here is going to be 3. And then from here to here is going to be 5, but my total radius of that circle is 8. So in order to find the probability that it will be in the inner circle, that's going to be the area of the inner circle divided by the area of the outer circle. So we're going to assume that the dart that you throw is going to hit inside the outer circle. So the area of the inner circle, so the area of that is pi r squared. The radius is 3. 3 squared is 9. So the area of the inner circle is 9 pi. Area of the outer circle, pi r squared. The radius r is 8. 8 squared is 64. 64 pi. If you want to make it simpler, putting it into your calculator, you can cancel the pi's. 9 divided by 64 is approximately 14%. So the probability that a dart thrown at random will land inside the inner circle is 14%. So in this section, we took a look at probability, experimental probability, theoretical probability, and how to use combinatorics to solve a complicated problem, and geometric probability.